Welcome to part 3 of building out the PETS algorithm with the Lunar Lander environment. In this video, we are going to go ahead and start working on our replay buffer class so that we can store memories and train in the environment. So we're going to call this memory.py, and we will need a few imports. We're going to import torch, and we're going to import OS. And I don't think we use NumPy in this one. I see I've got it imported, but I don't think it's in use. So we're going to go ahead and call it replay buffer is our class. And we will initialize it with a few different parameters. So we'll need the max size, the input shape, let's see, it's wanting to indent to self, so we'll just go ahead and go along with that and make this easier. And actions for the number of actions, input device, and output device will be CPU. And that should be everything we need there. And then we're going to remove the none. And we'll get rid of pass. So from a design perspective, what we're going to do here is we're actually going to pre-allocate all of the memory in the buffer. And then we're going to step through that memory with a memory counter. And that's just going to get all the memory pre-allocated up front. We're not going to be constantly increasing the size of an array. It'll tell us right off the bat if we're going to run into any issues. That's one of the reasons I prefer that design. So let's go ahead and say self.mem size is going to be equal to max size, and self.mem ctr is going to start out equal to 0. All right. And then one of the things that I've started integrating is the ability to put the replay buffer on the CPU or the GPU from an environment variable, depending on where you're running the replay buffer. I don't think that's really going to come into play in this video, although it might, depending on your size of GPU. But if you need to store more memory than what can fit on your GPU's VRAM, then you may want to push your buffer over to CPU. If you prefer not to store as much as possible on the VRAM, that will obviously be faster, and it can be a lot more performant. But that only works if your GPU has enough memory to actually hold things. So you can obviously just pass in CPU versus GPU, but I sometimes end up training on different machines that I'm writing the code on. So environment variables are better. So if you don't need that, then you can just ignore this whole part. So we're going to do override os.getEnv, and I'm going to call this replay buffer memory. And then I'm going to say if override in CPU CUDA 0 or CUDA 1, so a second GPU, then print received replay buffer memory override. And we're going to set self.input device equal to override. Else, we're just going to set self.input device equal to input device. And if you don't need this functionality, just go ahead and set input device to input device, and that's going to make things easier for you. And then we'll do self.output device is equal to output device. Simple enough. And then we get into our actual memories. So we're going to do self.state memory is equal to torch.zeros. And then we're going to do max size and star input shape. And then we are going to do a dtype equal to torch.float32, and device will be self.inputDevice, because remember, this is our actual storage. We're just going to copy this line, and we're going to call this our next state memory. So if you're familiar with RL at all, most RL environments are going to grab state, next state, action, reward, and then terminal memory or done. So that's what we're grabbing. We're grabbing our next state memory. And of course, the state is still the same size. So next state is exactly the same parameters as state. For action memory, we're going to do self.action memory is equal to torch.zeros. And this will be another self.memSize. Oh, we need another curly brace, or curly there. So paren, not curly brace. Self.memSize n actions. So we're grabbing something that is memSize long by actions wide, which makes sense. We're storing our actions. And then we're going to do dtype equals torch.float32, and device is equal to self.inputDevice. Okay. And then we're going to do self.rewardMemory. We'll store our rewards is equal to torch.zeros, max size, dtype equals torch.float32, and device is equal to self.inputDevice. And it was not a mistake that I did not add a double parentheses in there. All of the rest of these have been multidimensional. This is a single dimensional array of zeros. So all we need here is max size. Oh, and I accidentally copied that. All right, we're going to come down here. And very similarly, in fact, we can go ahead and copy and paste that and just make a couple of edits. We are going to grab terminal memory, and terminal memory is still going to be max size, but in this case, the data type is going to be torch.bool, because we're really just trying to store whether things are, done or not done, and bool is perfect for that. All right, we have established all of our necessary variables up here in the init method. Now we're going to go ahead and try or set up our can sample method. So we want the replay buffer to be able to tell the code that's interacting with it if we're in a place where we can sample from the buffer. And this is going to be a pretty simple method. We're going to say can sample. It'll take self and batch size. And then we're just going to say return self.memCounter greater than or equal to batch size times 10. So that's going to return the results of that. And what we're basically saying is if you ask for a batch size of 32, for instance, then we only want to say yes if we have at least 320 records. And this is variable depending on the project. In this case, we don't want a huge buffer. In some cases, I actually do, and I would set this a lot higher. So we're going to go ahead then, and we need store transition and sample buffer. So we're going to say def store transition will be self, state, action, reward, next state, and done. And then we're going to set our index equal to self.memCounter and modulo self.memSize. And let's talk about this again. I kind of explained it earlier, but what we're doing with this, so we've already up here, we've allocated the full size of each one of these buffers. This is going to be a giant array of zeros that will be, whatever, 10,000 long, for instance. The mem counter is basically just going to tell us where the latest memory spot is pointed to. So we're doing, it's not quite manual memory management, but it's probably about as close as you're going to get to it in Python. We're basically saying, hey, we're pointing to this one spot in memory, and then we're going to increment up every single time by 1. So why the modulo? Why not just say that index equals self.memCounter? Well, at some point, the mem counter is going to be higher than the memory size because we're going to, store 10,000 memories, and then we're going to need a spot to store more. So what this effectively ends up being is if mem counter, so modulo is going to return a remainder. That's what this does. So if, for instance, mem counter is 500, then index is just going to return 500. Let's assume that self.memSize is equal to 100. All right, so self.memSize is equal to 100. And let's say self.memCounter is equal to 80. We'll use that as an example. Then index is going to end up being 80. Makes sense, right? 80 divided by 100, you can't, you're going to get back, like your 80 is going to be what comes back. Or 80 modulo 100. I think you know what I mean. If you set 120, then what's going to come back after this operation is a 20. So it's effectively going to loop through the entire memory, and then this index is going to reset and drop us back to the beginning. And it will do this over and over again, effectively filling the memory and then rewriting it from the start. So that's what that little piece of code does, and it is a very important part of how this all works. All right, let's go on with our store transition code. We're going to say self.stateMemory, and we're going to look in index, and we're going to say torch.asTensor, and state dtype will be equal to torch.float32. Device will be equal to self.inputDevice. And that's a little long, so let's just go ahead and clean that up a little bit. And then we're going to copy and paste that and do the same with next state memory. And we'll do next state and just bump those over to make it all nice and clean. And then we will do self.actionMemory, and action memory index will be torch.asTensor. Next, not next state, we want action. Same dtype equals torch.float32. And device is equal to self.inputDevice. Okay. And then we want self.rewardMemory index, and this will be really simple, is equal to float reward. And then we're just going to copy that and do self.terminalMemory is equal to a bool of done. And I'm just lining this up with all the data types that we used up here. There's no real magic happening. And then self.memCounter is going to be incremented by 1. And my editor is complaining because I did not fully type terminal memory. All right. Finally, let's get down here and set up our sample buffer. So this is storing a transition. So the store transition method is basically going to store a single transmission. We're going to pass in a transition. We're going to pass in a single state, action, reward, next state, and whether or not the episode finished. That's done. And then the sample buffer is going to come in with batch size, and it's going to try to grab a batch of those memories so that they can be used for training. Makes sense, right? So we're going to go ahead and do def sample buffer, and we'll take self and batch size. And then we're going to say, we're going to declare our max memory. So max mem is equal to the minimum. So whichever value is lower of self.memCounter and self.mem size. Then we'll be grabbing our batch is going to be torch.randint. So we're grabbing a random block of integers between 0 and max mem. And what we're trying to do here is to not pull, we're saying, so remember, mem counter can go over mem size once it's reached because it's going to continue to increment. So we're basically saying if mem counter is lower than max size or than mem size, grab only values that have actually been populated. If it's higher, then grab any value in the memory. That's what we're doing here. So we're going to say max mem. And then we will say batch size. That is a shape parameter, if I recall correctly. And then we're going to say device is equal to self.input device. And our D type, our data type, is going to be torch.int64 in this scenario. All right, and then we will grab our states and next states. So states is equal to self.stateMemory batch, very similar. We're just grabbing our batch of states dot to, and this is going to be self.output device with a D type of torch.float32. And then we're just going to copy and paste that to next states. And instead of state memory, we're going to grab from next state memory. We'll just go down a little bit, give ourselves some space. We will do rewards is equal to self.reward memory. And that will also be batch.to self.output. Self.output device. And similarly, we are going to do dones, and that's going to be terminal memory in a batch to self.output device. And then we will do something very similar with actions. So that'll be action memory. This should start to look very, very similar with our batch of indexes. And then we're going to do a couple things to make sure that the shape is always correct. So we're going to say if states.dim is equal to 1, states equals states.unsqueeze. And this may not be necessary anymore, but it made it in there. And I'm not going to remove it and potentially add bugs. So we'll do the same thing with actions is equal to 1 and actions equals actions dot unsqueeze 0. All right, and then finally, we're going to return states, actions, rewards, next states, dones. All right, this is a really good moment to stop and really read through the code. I have run into many hard to trace errors or issues where the agent wasn't necessarily learning, but it wasn't throwing any obvious errors. It was running, it was processing, it was trying to learn, but it wasn't going anywhere. And those bugs have frequently traced back to me either setting next states to state memory, or something like that, or, rewards to dones, some scenario where I was returning the wrong values for one of these, and it throws the whole equation off. So take a moment, really read through this. It is important. And then just as a little helper method, let's go ahead and do def print mem size self, and we're going to grab something really similar to the logic up. Let's see. We're just going to grab this max mem param and say print currently max mem records loaded in the buffer. And we won't run that all the time, but it is going to be useful in a little while for troubleshooting. All right, so we just typed a whole bunch of code. Let's go and integrate it and make sure that this all works the way we expect it to and that we don't have any problems. So we're going to start off in our agent over here. And inside agent, we're now going to need a few more variables. So we're going to grab obs and info from env.reset. And the reason we're doing this is I really don't want to, I don't want to hard code values. Anywhere possible, I want to try to grab the necessary values for things like memory and our network directly from the arguments in the code base. So what our goal is here is to grab everything we need from the environment. And that's probably another good place to stop and throw a little challenge at you. And I'm going to give you the first part of several chunks of code here. So action equals self.device equals and self.memory equals. So what we're looking for is memory will hold the replay buffer class, which is going to take a series of inputs. We just created it. You should be able to go find the inputs. Device should land as CUDA 0 if CUDA is available on your system. There's a simple check you can use for that. And then action is going to be a sample of the environment action space. So I just gave you a few hints. Pause the video, go take a look at that, see if you can fill in these three values and get it working. If you have it at a point where these are filled in and the code runs, you're probably in an okay place. All right, pause here, and I'll wait. All right, hopefully you had a chance to run through and get that working. If you didn't, or if you did and you'd like to see my answer to it, let's go ahead and start. So we are going to need to first import. So from memory, import replay buffer. And then down here, we're going to grab our action from env.actionspace.sample. I did say we needed to sample the action space. We're going to set our device. So the easy way to do this, you could obviously just hard code it to CUDA 0. But what you really want to do is say CUDA 0 if torch.cuda.is available, else CPU. That way it's a little bit more resilient. And then our memory is going to point to replay buffer. And we're going to do max size is equal to self.max memory size. We already took that in. Our input shape is going to be obs.shape because we got the observation. So now we can pull shape information from it. Our n actions is going to be action.shape and 0. And our input device is going to be self.device. And in my case, my output device is also going to be self.device. If you have a less heavy GPU, if you're running something that can't handle 10,000 memories, then you probably want to set input device to CPU and leave output device set to self.device, which if everything is set up correctly, will be CUDA 0. That's probably a good point to note. Let's come over here to memory, and we're just going to say we're going to add some logging here that says something like let's do replay buffer created on device self dot. We need a little bit better logging, don't we? With input device self dot input device and output device self dot output device. I just want a little bit of information so we can see if things like if it is successfully going to the GPU, because if it's not, it could be a lot slower, and we really don't want that. All right, let's go ahead and run this. It's not going to be doing anything with the replay buffer, but it should at least tell us if it, is failing, and it's not. So you'll notice down here, we get this nice little message, replay buffer created with input device CUDA 0 and output device CUDA 0. So that is working the way we expect it to. Let's go ahead, and the last thing we're going to do is during train, we had a to-do down here that says store memory transitions. So we are actually going to go and do that. So here we're already accepting a bunch of data from self-env step. Let's go ahead, and down here we're going to say self.memory.store transition. We've got a method for this, and we're going to pass in obs, action, reward, next obs, and done. All right, and we're not going to leave this code in, but we are going to go ahead and say, you know what, we won't do it here because that's just going to be a little bit too verbose, but I'm going to tab in one or tab out one. And then down here, we're going to do memory self.memory dot, and then we had a method, print mem size. That's what I'm looking for. And just get it to, oh, I messed something up there. I lost the change we just made. All right, let's redo that. I accidentally closed out my editor without that change saved. Hopefully I didn't lose anything else. Let's see. So we're going to do self.memory.store transition, obs, action, reward, next obs, and done. All right, and up here, okay, cool. We didn't lose that. And down here, we are going to do exactly what I was just saying and say self.memory.print mem size. And what this should do is every episode, it should give us a current memory size, and that should tell us that our memory is growing over time. So let's go ahead and test it. All right, our episodes are running, and we can see 64 records loaded in buffer, 205, 330, 462. That certainly looks to me like we are successfully filling our replay buffer over time. All right. We won't be able to test the sample method, at least not suitably, because we're not in the training phase yet. So in the next video, we are going to go ahead and start building out the initial base model that we're going to train, after which we will work on the ensemble of models. As usual, there will be a GitHub link with a link to the tag that is associated with the code as it sits at the end of this video. If you aren't getting the same results that I am, go take a look at the GitHub, and I hope you'll join me in the next video.